Hello, welcome back to these lectures on physics. We have already studied the concept of work and energy. We have also introduced kinetic energy, which is the energy an object has due to being in motion. But we have not mentioned yet any relationship between time. Think about the following example. You're driving a car on a motorway. To get into the motorway, you need to accelerate to go from 0 to 60 miles per hour. You could do this acceleration in 20 seconds, or you could do it in 10 seconds. Probably if you had a high-end sports car, you could do it in 5 seconds. If the mass of the three cars is the same, and because the initial and the final velocities are the same, all three cars gain the same kinetic energy, so the work done is the same. But in each one of the cases, that work is done in a different interval of time. This last case requires a high-power engine. We define the power as the rate of change of energy, or the rate at which work is done, the rate at which we transfer, we consume, or we use energy. Mathematically, we can write this as power equal to delta work divided by delta time. This, in the limit of a short time interval, as usual, will be the derivative of work with respect to time. The units of powers are joules divided per second, which gets the name of watt. We can back-engineer this expression and write that the work done is the integral of the power with respect to time. Let us solve a problem involving power. Consider one of those old television sets that were like big boxes. Inside them, electrons were accelerated uniformly from rest to a speed of about 8.4 times 10 to the 7 meters per second, over a distance of 2.5 centimeters. Let's calculate the power delivered on the electron. From the definition of power, we need to calculate the work done on the electron in the time that the force is acting. The work is the force times the distance, and the force is the mass of the electron times its acceleration. So first we need to calculate the acceleration. We do this from our knowledge of kinematics. We use the equation that relates the final and initial velocities with the distance traveled and the acceleration. We get that the acceleration of the electron is 1.4 times 10 to the power of 17 meters per second squared. The mass of the electron is 9.1 times 10 to the negative 31 kilograms. We need to calculate also the time of flight of the electron. From the equation of motion for a constant acceleration, we have that delta x is equal to 1/2 at squared. From this, the time of flight is the square root of 2 times delta x divided by a. This gives us 6.0 times 10 to the negative 10 seconds. Finally, we substitute this into the equation for the power, and we get that the power is 5.31 times 10 to the negative 6 watts, or 5.31 microwatts. The tally has done a work on the electron of 3.19 times 10 to the negative 15 joules in an interval of 600 picoseconds.